Okay, so let's review the differential in Z real quick here. And we said that was, and that, so that the differential in Z just was, really didn't feel like anything new because it was what we talked about with partial derivatives the whole time, that given any change in x, the resulting change in Z is just the partial derivative times the change in x. And so say we're at the point AB, okay? So say we're here at AB. So remember that that was how we framed the meaning. We've been saying this like for the last 4 or 5 class periods. Given any change in x, the change in z is the partial derivative times the change in x, right? And that frames the meaning for a rate of change. And so we have the same thing for y. Given any change in y, the resulting change in z is the partial with respect to y times that. And so the differential then would be the total change from both a change in x and a change in y. So we can just add them together. Okay, and so we said that, so looking at, and that was, the change in x then was from the point AB, so the change in x would be x minus a, x being any point close to x and y being any point close to AB, and then the change in y would be final minus initial y minus b. So x and y are variable. You could pick any point around there, and then by applying this formula here, we get the change in z, the differential for your new point xy. So what if we wanted to predict what the new z value is? So the change in z is something like this. And we know it's an estimate, right? It's an estimate because this is based on linear constant rate of change or linearity of the partial derivatives. So there's our dz. What if we wanted to predict this new value of z, right? We have the original value of z, which is f of ab. We have the change in z, which is our differential. So how can we use those then to predict the new z value, right? The new z value at the xy point a little bit away from AB. What would we do?
Integrate?
No, we got the original z value, and then now we have this expression for the change in z from AB to xy. So if you have initial z and a change in z, how do you write the new z?
AB plus DZ. Add them.
Yeah, you just add them up, right? You just add them up. You take the change in z, the change in z, and all you need to do is add the original z to it, and that will give you the new z. And that's going to be, again, it's going to be approximate. It's not going to be the actual value of the function. It'll be approximate because this change in z, our differential, is based on linearity, where the surface is actually curved, right? So differentials, we saw an example with the ice block we can use to predict like a change in an output variable based on changes in the input using the partial derivatives. We can also use the differential to estimate the new value of z by adding the differential to the old value of z. So that should make sense. Let me just, while we're talking about differentials, there's a question in the homework. That has to do with a cylinder. And so they're talking about the cylindrical can, And they talked about, and so what they're getting at in this problem is about the amount of material, amount of metal to make a can, like a hollow can, right, that holds green beans or, you know, whatever, pears or whatever like this. So, so it's based on the volume of the solid cylinder, which is pi r squared h. So if you have the solid cylinder, that's all filled in. Imagine that's all filled in with metal. It's heavy, right? It's heavy because it's all metal all the way through. What would dV represent? Well, dV would be if you change the height and radius a little bit, how much new volume would you get? What's the change in volume, right? And so I can show that here like this. So we're increasing R and H. And you're going to add some metal to this solid cylinder. Well, if you only consider how much you added and don't consider all the original solid cylinder, just how much you added, well, that's a way to model, that can model the amount of metal that makes up a hollow can. Do you see that? So the amount of metal added to the solid cylinder forms like a shell with a little bit of thickness that can model the volume of metal of a hollow can. And that's what they're getting at there. So you start with your volume function is of a solid cylinder. dV would be like if that thing grew a little bit, how much volume was added on, increased by. Well, that's a good model for the amount of metal for a hollow can, kind of like what I'm showing there. Does that make sense? So that's just to get you in the mindset for that web work problem. Okay. So. Okay, so let's go back to let's close that out. So here we are back in here. So again, we got the differential. It's the change in z using the partial derivatives. And then we can use that differential to estimate the new z value by adding the old z value to the amount of change, which is the differential. So we're going to hold on to that. We're going to kind of shift gears for a moment here and take a look at something else. But this is an important result here, or important use of the differential to estimate the new value of z. Any questions on that? All right, so now what we want to do is we want to look at this line right here. So here's a line tangent to the surface. And what else do you notice about that line? There's many lines tangent to that surface, but this one has a special feature. Anyone see what that is? In terms of its like kind of orientation here. I can top it right there. What's special about this tangent line?
Is it the slope of z increasing?
It is, and that's what makes it a tangent line. But so yes, it's tangent to the surface, so it's like kind of modeling how z changes right there. But specifically modeling how z changes.
It's along the xz plane, right?
Right. So this is the.
It's only with respect to changing that.
Right. This is the tangent line to the surface. Parallel to the xz plane, or in the x direction. Okay, so this tangent line to the surface, but parallel to that xz plane. So we're going to write the equation of that line. And what is our equation of a line? In today's class, we're going to pull back from a lot of stuff we did in exam 1. Okay, so tangent line is a point. So this is the vector form. Point plus all scalar multiples of parallel or orthogonal vector.
Orthogonal.
So to write the equation of a line, we need a vector orthogonal to the line. Is that right?
Yeah.
Uh-oh. No, there's lots of orthogonal vectors. You know, so for given an orthogonal vector, there's lots of lines that have that orientation. This needs to be a parallel vector, right? For a line, we need a parallel vector that gives us the direction of the line. Okay? Not orthogonal. All right, so we have the point, because this is still our point, say AB. And then our point on the line will be A, B, f of AB. So all that's left is we need a parallel vector. So right off the bat, is there any of the components that we know right off the bat for this particular line that we can write down?
Y has to be 0.
Someone said y is 0. Agree with that?
Yes.
Yes. There's no change in y parallel to this line, right? If it's parallel to the xz plane. Oh my gosh. Oh boy. Oh, that was a pretty good recovery. Stop. Wow. Out of control. Okay. There we go. Yeah, so there's no change in y. If this is parallel to the xz plane, there's no change in y. And so my y component of that parallel vector is 0. So now what's left, I need the x and z components of this vector.
Is the green arrow going to the right below y?
Yeah, this is y and x.
Oh, I got them mixed up. Okay.
Yeah, this is kind of like our standard view of things, right? X comes out at us and y goes to the right. So how are we going to get the x and z component of this line? Say like this.
Could you use 1 and then the partial derivative of z with respect to x?
All right, so good. So we need a change in x and a corresponding change in z. We need these in right proportion to get the inclination of this line, right? So that you get this line. And so what is the proportion of dz to dx? What is that?
Partial derivative.
That's the partial derivative, right? That's the partial derivative. And so we know about the partial derivative. We can choose for any value of any change in x that we pick. Here it is again. Here it is again. For any x that we change in x that we pick, the change in z is the partial in x times the change in x that we picked. So there's no requirement for the magnitude of this vector. We just need x and z to be in the right proportion. So we can pick dx to be anything we want, and the gentleman made the best choice. What's the easiest choice we can make for dx? 1. So if, on this line, if x changes by 1, then, according to the partial derivative with respect to x, how much does z change?
That's partial of x.
Partial of x, right? So that gets us our vector that's tangent to the surface, but also, in the x direction, parallel to the xz plane. Okay, and so then...
Sorry, that would be the partial of x at AB, right?
Yes, exactly. I just ran out of room. It would be only the partial, partial of x is a function. We want it at AB, exactly. Yep. All right, so then what about another tangent line? We can do another tangent line similar to that. And that would be in the y direction, parallel to the yz plane. So then you do a tangent line parallel to yz, y direction. Okay, and so that would be same point. Plus Now, what do we know about that line? So this red line, what do we know right off the bat about that line?
X has to be 0.
Yeah, the x component is 0. There's no change in x if it's parallel to yz. And then we want to get what? We want to get a vector. We need changes in y and z according to this line, which we're getting from a tangent to the function. So what are we going to do? We're going to let dy be 1, right? Change in y is 1. And if the change in y is 1, then the change in z is the partial derivative with respect to y at ab. Maybe I can fit it this time. Made it. It's the partial derivative with respect to y. Okay, so we wrote the equations of both those lines. We got our point on the point of tangency. We figured out what the direction vectors were. And so there's a plane. There's a plane that contains those two lines. And what would be special about that plane for our surface?
Defined by points.
So let's draw that plane. So there's the plane. No. There we go. So there's a plane that contains both those lines. So, and both the lines are tangent to the surface. Therefore, the plane is?
Tangent to the
It's the tangent plane, right? So this is the tangent plane to the surface. We're going to write that equation. So the generic, our basic tangent plane equation is a times x minus x naught plus b times y minus y naught. This is when you have a point, and then how do we get the orientation of the plane? What's our ABC vector? Is that parallel or orthogonal?
orthogonal.
This one's orthogonal, right? The inclination, the orientation in space of a plane is locked down by a vector orthogonal to that, not parallel. So let's stop this spinning here. Right there is good. Right there. No, didn't happen. We're gonna wait for it to come around again. There we go. And stop. Okay. No, stop. There we go. So our point, we got our point still, is the point of tangency, A, B, and f of AB. So then the so the question is, what is the orthogonal vector? How are we going to get the orthogonal vector to this plane? That's our ABC.
Orthogonal to the other.
It's going to be orthogonal to this line, and it's going to be orthogonal to both lines. Therefore, we're going to use the cross product. We've seen this before. We use the cross product of the parallel vectors to those two lines, which will be orthogonal to both of them, and then therefore orthogonal to the plane. So here we go. So we're going to do the cross product. Just ijk, and then what? 1, 0, fx, 0, 1, fy. All right, so we're going to do our cross product, which means what? Down to the right 3 times, down to the left 3 times, and add and subtract. So the I component will be, so this will be down 0, and then down to the left, negative f of x, or negative fx. And then the j component down to the right is 0, down to the left is negative partial with respect to y. The k component down to the right is 1, down to the left is 0. So there's our cross product. And so this vector is orthogonal to the plane, and we can use it to write its equation. So here we go. Negative fx ab times x minus a plus negative fy ab times y minus b. So So now this A and B is our coordinates of our point, right? So A, B, so I've got keep those straight. There's the x and y coordinates of the point A, B, and then there's the x and y components of the orthogonal vector A and B. So those are different things, but once we get it all filled in, it's okay. And then plus C is 1 times Z minus f of AB. That all equals 0. So what is this? This is the equation of the tangent plane at the point AB and f of AB. We got our orthogonal vector, boom, 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 and then we got our point AB, f of AB. Now I'm going to take this equation of the tangent plane, and I want to solve it for z. I want to get it kind of as a multivariable function, right? I want to get it as z as a function of x and y. So that means I want to solve for this right here. So z equals. So that just means I got to move this whole term over, add this to both sides, move this whole term over, add both sides, and then once I'm done with that, just add this. So here we go. So it's going to be positive fx ab times x minus a plus positive fy a minus b plus f of ab. And so
that looks like it's giving you the same approximation as before, right?
Aha. So okay, good. I'm glad you noticed. But this is not an approximation. This is the equation of the gray plane. Okay? So this is the tangent plane as a multivariable function, as a function of x and y. Okay? But he noticed something, right? And so maybe some others of you noticed this too. What do you notice what's familiar about this equation?
Yeah, like I said, it was similar to the one we got with the differential, right?
Right.
But
And
actual equation.
what was that? That was before when we did that, we got the same expression. It was for what? What was it that we got, what that we were talking about that we came up with this expression for?
Tangent, or dz.
The what?
dz.
No, dz was part of it. So these first two terms were the dz. But then we said we took the dz and we added the original function value.
So the final z after we add z to dz.
Yeah, it's the new. It was an estimate for the function value at xy. We started at ab. We moved away from ab a little bit to some point xy. And this expression was an approximate for the value of the function at xy based on the derivatives at AB. So this expression is the tangent plane, and it's also an approximation for the new z value. So why does that make sense? Well, it's because for points x, y close to AB, the tangent plane is very close to the surface, right? And what do we say about this using the differential? The differential is based on constant rate of change of using our partial derivatives. We get a linear approximation because the partial derivatives are based on, it's a linear phenomenon, right? And so
should the equation be fy a of b times y minus b, not a
yeah,
minus
that should be y. Yep. Okay, so the tangent plane for values close to A, for ordered pairs close to AB, is the linear approximation of the function values. And so that's why it came up both ways. So when we figured out the tangent plane, we got this. When we figured out our approximation for z values, we got the same expression. And it's because when you're in the neighborhood of AB, all the xy points in the neighborhood of AB the tangent plane will give you a good approximation. It'll be really close to the z values of the actual surface. But if you move away, if you move too far away, then that plane, the plane deviates is well away from the surface. So it's not a good approximation. But it's still the tangent plane. It's still a legitimate surface on its own. It's just not a good approximate. It doesn't do a good job approximating z values of your surface. That only happens close to. So if I turn the surface a little bit, oh man, you can see that when you there we go. That's a good view. So close to the point, see that tangent plane hovers close to the surface. Move away from that point, the tangent plane's way out here, the surface is way back here. Big gap, big error. Okay? So the point is, and then the tangent plane, so when we use the tangent plane to estimate values of the function, we call that the linearization. So this thing, instead of saying z, we can say Lxy for linearization. The linearization of the surface at the point AB is the tangent plane, and that provides good estimates of z values close to the point of tangency. If xy is close to AB. And close would be relative to your situation, right? If you have a really flat surface already, then you get some more, you could be a little further away and you still might be okay with your approximations. But if the surface is curved very severely at your point of tangency, then you need to be really close. You need to be your xy needs to be really close to AB in order for the linearization to give you a good approximation. Okay, so questions on what's called the linearization. So the tangent plane is the linearization of the function at that point. So we call it Lxy. Again, it's still a valid function away from the point as a tangent plane. It's just, it doesn't then serve as a good way of approximating z values because you're too far away from AB. Any questions? Okay, so let's go back to a different conversation that we had before. If there's no questions.
I have one question.
Sure.
Is this always going to be an overestimation for a concave surface?
Concave, I guess if it's concave down, your linearization will give you the values of z will be too high, right? And if it's concave up, then the linearization, the tangent plane will give you z values a little bit too low. Does that answer it? Does that make sense?
All right, that makes sense.
Yeah, I think that's true, yeah. Okay, so let's look at, I did this here, let's turn that off. Go back to number 1. Another probability to term, let's see. Okay, so I got a point on this, here's a multivariable surface, say function f. Oh, I was doing so good. And I got a point on that surface, kind of back there. All right, and so I want to just review predicting at that point on this surface f, so this is surface f, what could we say about the partial with respect to x? Say at this point, x naught, y naught? So if this is x naught, y naught, and the partial with respect to y at x naught, y naught. So x first. What could you say about the partial with respect to x at this point? What do you think?
It's negative.
We have a vote for negative.
Great. Negative. I second.
Yeah, so so let me, and I'll show you a constant. I'll give you a, no, return here. So there's holding y fixed. If you let x increase a little bit, what does z do? Does it go up or down?
Down.
Goes down. First partial is negative. Okay, similarly, if I hold x constant,
Y will increase.
y will increase. He says y will increase. Agree with that?
Yes.
No, sorry. If we hold x constant, we let y increase, and then we ask about z. So y, if y increases, what does z do?
Increases.
Going up. Going uphill, right? We're going up. We're going up. Therefore, partial with respect to y is
Greater than 1. 0.
positive, right? Positive, exactly. Greater than 0. Okay, so that's a little bit of review. And so now we want to talk about, in your homework, you were doing some just algebra, purely deriving some second derivatives. And I know that you're very smart and could do that without me doing examples in class, because f of x is just a new multivariable function, and then you're taking the partial of that function with respect to x. And so this is a second derivative. So we're going to talk about what these, and then similarly, fy is a multivariable function. Take its partial derivative with respect to y, and you get the second. So these are two of the second partials. There are actually 4. You got fx y, and then fy x. And you're simply taking your first partial derivatives functions and doing partial derivatives again. So that gives 4 combinations, right? Gives 4 combinations of x and y. So these are the second partial derivatives.
Question.
Yeah.
So with multivariable functions, it's fairly similar to the other ones. This would give just like we learned in Calc 1D and.
Oh, we're about to do it. We're about to do all this with the second partials. Yeah. So just hold your horses. We're about to talk about the concept here. Yeah. All right. So let's investigate this here. Clear all drawings. And we'll go over here. Here. Okay. So these are the second order partial derivatives. We're going to talk through this. So let's first talk about the second partial x with respect to x. Okay? Or just fxx. So what does that reveal? So this is going to reveal how the rate of change with respect to x is changing with respect to x, right? So the first partial with respect to x tells us how z changes, or the function value changes with respect to x. Then the second derivative tells us how the first derivative, or f of x, changes with respect to x. So all the same relationships that we had between x and z and the first partial derivative, all those same relationships apply between x and the first partial derivative and the second partial derivative, because it's just taking the derivative, okay? It's just the rate of change, but now it's the rate of change of the rate of change. So all the same relationships still apply. So for instance, understanding the second partial with respect to x means given any small change in x, what's going to be true? So now we're asking about how much the first partial derivative changes, not how much z changes, but how much the first partial derivative changes, and that's going to be the second derivative times as much as dx. So this is exactly the same thing we did before, but just like up one level, right? Everything's up a level. We're still going to change x a little bit, and then the change in the derivative, or the change in the rate of change, is going to be the second derivative times as much as our change in x. Okay, so this is telling us, the second derivative then tells us how the first derivative, or how the rate of change, is changing. So suppose, let's talk about the case where the second derivative is greater than 0. So if the second derivative is greater than 0 for a change in x, what about the change in the first derivative? It's also going to be greater than 0. And if the change in the first derivative is greater than 0, what could we say about the first derivative? If you have a change in something that's positive, then what's happening to that quantity?
Increasing.
It's increasing, right? So the second derivative being greater than 0 means our rate of change in the x direction is increasing. And there's two ways that can happen. There's two ways that a rate can increase. Either it can get less negative, so here's a highly negative rate, and it's getting less negative as x increases. That's one way a rate could increase. The other way the rate could increase is if it gets more positive. So shallow, steeper, steeper, so the rate's getting more positive. But in either case, as x increases, the graph is turning up, right? As x increases, the graph turns up. The rate's getting less negative, the rate's getting more positive. That means the graph keeps turning up. The rate of change is increasing. And that's what we get for the second derivative being positive. And so this is what we call concave up. I just like turning up better because you're thinking about as x increases, what's happening to the rate? The rate's getting less negative or more positive, and that creates a graph that turns up. Does it make sense? So, yes, the question that the gentleman was starting to ask me is absolutely true. So the second derivatives, it's just now we have four second derivatives, but we're going to focus on two of them. So we have a concavity or changing rate in two different directions that we can consider. So this is in the x direction. And then let's talk about when the second derivative is if the second derivative is less than 0, what can you conclude for an increase in x? If the second derivative is less than 0, your change in your first derivative will be negative, which means what about the first derivative? If change is negative, it means your rate of change is decreasing. So when the second derivative is less than 0, the rate is decreasing, and there's two ways that can happen. Either the rate's getting less positive, so higher rate, lower, lower, lower positive rate, or the rate is getting more negative, greater and greater negative rate. That's all a decreasing rate. So in that case, the graph is turning down as x increases. As x increases, it's regardless of whether z is going up or down, it's always bending down, right? Turning down. That's the rate decreasing, and that's when we're going to have a second derivative less than 0, and that's our concave down situation. Okay, so let's look at some examples in the graphs of this. So going back to this, so let's look at this first example again. Let's choose something a little different here. How about gold? There, that's better. Okay, so what about this is for the partial with respect to x or respect to y, what I'm showing here?
Y.
Y.
Yeah, so I'm holding some. So what did we say the first partial with respect to y was here?
Negative or positive.
This is positive. For a change in y, z goes up. We're heading uphill. That means the first partial is greater than 0. But what about the second partial? So now we're asking, what does the rate do? Is the rate increasing or decreasing?
Decreasing.
Decreasing.
Decreasing. It's getting less positive, right? We got a high positive rate, but then a lower and lower and lower positive rate through there. So the rate of change is decreasing, therefore the second derivative is?
Negative.
Negative, less than 0. And then you can see that the graph turns down. It's concave down because the rate is decreasing, so the second derivative is negative. All right, first derivatives on this one. I guess we can leave it right there. So we said the first partial with respect to x was?
Negative.
Negative, because if x increases, z goes down, right? You're just heading down. That's the first derivative. And then what about the rate of change? So the rate of change is negative, like we said, and is it getting more negative or less negative?
Less negative.
More negative.
It's more.
More negative.
Oh,
It's getting steeper in the negative direction. So is that increasing or decreasing rate?
Decreasing.
Decreasing rate, right? Decreasing rate of change. Therefore, second derivative is?
Negative as well.
Yeah, that one's negative. Okay, one more example, and then we'll take the quiz. All right, let's see here. Next example, this point over here. Let's do x first. Let's see if I can just turn this without blowing it too bad. All right, let's try right there. So in the x, I'm going to turn some more. Oh, no. What have I done? Lucky. Okay. So here's in the x direction. Is the first partial with respect to x positive or negative? That's what does z do, right? As x increases, does z go up or down?
Down.
Down. Here's my y-axis, here's my x-axis. Going down. First partial, negative. What about the second partial with respect to x? So now we're asking about the rate. What's the rate doing along here? Increasing or decreasing?
Decreasing.
Decreasing, getting more negative. What's the rate doing over here? Increasing or decreasing?
Increasing.
Increasing. So right in between those two, there's a point where the rate kind of stays constant for a moment. It's kind of like a linear for a moment. And so the rate isn't, for one moment, the rate changes from decreasing to increasing, and it's not changing. Therefore,
Zero.
this is our inflection point. So the second derivative is approximately 0 because it's not, the rate is no longer decreasing and ready to start increasing. But right there for a moment, the rate is not changing. It's like a linear spot. Okay? Why? Is there questions on that? Does that make sense? So that's the same as your inflection point in Calc 1. So going down, so first derivative is negative, but kind of flattening out for a moment there. So second derivative is about 0. Let's see if I can turn this without making a mess. Maybe. Not bad. So what about the partial with respect to y? Turn this one off. How about the first partial with respect to y? So if we let y increase a little bit, z going up or down, or maybe staying the same?
Stay the same.
Yeah, it looks like it's kind of staying constant there. It's like we got like a local minimum, right? In the y direction. Pull this down a little bit. There we go. That's pretty good. Yeah, so it's like kind of, z doesn't change. For an increase in y, z kind of stays the same. It's a local minimum in that direction. Okay, what about the first partial with respect to y? Second.
It's increasing.
Yeah, so we're getting, rate of change is getting less negative to more positive, right? So the graph is all through there, the graph is turning up, right? Rate is increasing. Positive second derivative. Because the rate's getting less negative, more positive. Concave up, turning up, positive second derivative.
Why is f of y of x null, y null approximately 0?
Because this would be about, if you increase y a little bit, how does z change? How does the height change? How does z change?
Is it not increasing?
No, it's pretty close to staying constant. You see that?
Increasing in the y direction.
In the y direction. In the y direction. So if you go in the y direction, this way, it's pretty flat here. See that? Can you see that?
Kind of.
Right, because this is kind of like the along that x value as y changes, the point is kind of at the low point. It's heading down before it, and then it starts heading up. So at the low point, your change in z will be minimal. So the rate of change is 0.
Okay.
You buy that?
Yeah.
Okay, go take your quiz.